Hello, all of you. Welcome to this session. My name is Prasanjit. Usually, I like to talk a lot about cloud, especially Google Cloud. So today is no different, and I'd like to talk about Google Cloud Platform. And this will be short, but I'll try to cover the entire Google Cloud Platform in a matter of few minutes. So after this session, what will happen? You will know how to get started with a Google Cloud account for free. You will learn how you will be able to reduce costs in your GCP infrastructure. What are the tools, tips, and tricks to use there? You will learn how to organize your resources in Google Cloud Platform. You will learn to automate the creation and configuration of your resources. You will learn how to manage operations, logging, monitoring, tracing, and so on. You will learn how to store your data and where to store your data in GCP. You will learn how to deploy your applications and services and what are the tools to use to do that in GCP. And you will learn how to create networks in Google Cloud Platform and connect them with your on-premise networks. And it doesn't end there. You will also learn how to work with big data, AI, and machine learning, and finally about security. So basically, you can consider this as a crash course into Google Cloud. So this will give you a surface, a brief level idea of everything that you're going to encounter when you, say, do a basic task of hosting a website or application on Google Cloud. So this gives you a primer on Google Cloud Platform. So in order to get started with Google Cloud Platform, GCP offers a 3-month free trial with $300 of credit, and you can use that to get started and start playing around with GCP, and you can run your experiments and to decide whether this platform suits you or not. And obviously, I recommend Google Cloud Platform, and it's very convenient and productive and effective for most cloud tasks. And in the end of your trial, you would not be charged. You will be notified that your services will stop running unless you decide to upgrade your plan. So pretty safe. And I recommend you using this trial to practice, learn. And once you learn, you face problems, break things, and then fix them. And that's how learning goes. And it doesn't matter how good this video is going to be or not, but if you try it, it is not going to harm you. So what makes Google Cloud Platform special, and why would someone try to migrate their services on Google Cloud Platform or even bother to learn about GCP? Well, there are lots of benefits here in GCP. You don't have to spend a lot of capital costs for hardware in order to deploy your services here. You do not need to upgrade your hardware, migrate your data services every few years. That is managed by the Google Cloud. And you have the ability to scale and adjust to the demand, paying only for the resources that you consume. And you can create your POCs quickly, and it takes just a matter of minutes to provision resources in Google Cloud. It is secure, and you're able to manage your APIs well here with different tools that GCP provides. And not just your infrastructure, data analytics and machine learning services are very advanced in GCP, and makes it very easy to experiment and use the resources you need in an economical way. So these are the reasons basically, and there are many more reasons and advantages of Google Cloud in comparison to other public clouds. We'll come to that in other videos or somewhere down when we find a certain use case. All right, so how do we optimize our VMs to reduce costs in GCP? All right, so in general, you would be charged for the time your instances are running, But Google Cloud does not charge you for the stopped instances. However, if the consumed resources like disks or reserved IPs, you might incur charges. But if they are just stopped, you do not. And here are some ideas, like let's talk about some ideas in which you can optimize the costs of your applications in Google Cloud Platform. So one of them is you can use custom machine types. So GCP provides different machine families with predefined amounts of memory and CPU. So you can use a general purpose VM, which offers the best price performance ratio for a variety of workloads. You can use memory optimized VMs, which are ideal for memory intensive workloads, for applications that use more memory. You can use compute optimized for higher performance per core for compute intensive workloads. For example, say you are running some queries on your database and so on, which are hosted on virtual machines. So you can use compute optimized, and you can use a shared core VM. These machines time share a physical core. So the CPU time is shared between different stakeholders, and this is cheap, but you can use that for running less intensive or important applications or smaller applications in your stack. So that way you can use the custom machine that suits your use case, so that you end up paying less. Now there is another kind of VM that is called Preemptible Vm. So you can use preemptible virtual machines to save up to 80% of your costs. So let me tell you what use cases these are ideal for. These are ideal for non-critical applications, those that are fault tolerant, and you can save the progress of your job in a persistent disk just in case the preemptible VM shuts down, and continue when a new VM launches from where you had left off. So Google may stop your instances at any time with a 30-second warning, and will always stop them after 24 hours. So but on the other hand, you save 80% of your costs. So if you can wisely use the preemptible VMs, you're going to save a lot of money. So to reduce your chances of getting your VM shut down, Google recommends you use small instances and run your jobs during off-peak times. Now, you should remember that startup and shutdown scripts apply to non-preemptible VMs as well, and you can use them to control the behavior of your machine when it starts or stops. So just in case you want to sync your data to somewhere else before the VM stops, or you want to pull data from some storage when your instance starts, or you want to mount and unmount a certain storage when it stops or starts, you can do that. You can define them in the start-stop scripts. And using these wisely, you can really save a lot of money when it comes to virtual machine or compute costs. And it also, I mean, you can have sustained use discounts, where the longer you use your virtual machines or Cloud SQL instances, the higher discounts you will get. So in this way, you are earning yields or the discount that you get. So the longer you run your VMs and Cloud SQL instances, the more discounts you get. So this is a very good thing that Google automatically provides for you. And Google also provides for you committed use discounts, which means you can get up to 57% discount if you commit to a certain amount of memory and CPU resources for a period of 1 to 3 years. Like you reserve your instances and get discounts based on that. So these are some of the ways in which you can save money when with your compute resources on Google Cloud Platform, and some of the reasons why you should go with Google Cloud as compared to other cloud providers. Well, so that was about how to save money and why you should be on Google Cloud. Now let's quickly move on to how we manage resources and administer our accounts on the Google Cloud Platform. Well, the Google Cloud resource hierarchy looks something like this. Now, there are 4 types of resources that can be managed through Google, through the resource manager in Google Cloud: the organization resource, the project resource, the folder resource, and the other resources. So org resource is the root node in the resource hierarchy, and it represents an organization, for example, a company. And then you have the project resource. So you have different projects for production and development environments and so on in your company. So these are, they are required to create the resources. And then you have folder resource, where you can have extra level of project isolation inside the projects. And then inside folders, you have components which cannot be further divided, like the virtual machines, database instances, load balancers, and so on. So very simple. This is how the hierarchy, the resource hierarchy stands. And then we have quotas that limit the maximum amount of resources that you can create. Now, quotas also help you prevent unexpected spikes in billing. For example, you ran a script with spawned auto-scaling group of virtual machines, and with load or with some test script, load testing script that was going on, you spun up a huge number of VMs and ended up paying for that. But with the quotas, you provide some kind of guardrails to prevent the maximum number of resources that can spin up, so you can prevent unexpected spikes in your bills. However, one must remember that most quotas can be increased by raising support tickets. All right, so let's move on and discuss about how the resources in GCP follow hierarchy via a parent-child relationship, similar to what we have in a traditional Linux file system. So the permissions are inherited as we descend the hierarchy. For example, permissions granted at the org level will drip down to folders and projects. So top-down propagation of permissions, and the more permissive parent policies always overrule the more restrictive parent policies. So that is keeping the security in mind. So if parent policies are permissive, then they will overrule the restrictive child level policies. Now, the hierarchical organization helps you manage common aspects of your resources, such as access control and configuration settings. Now, you can create super admin accounts that have access to every resource in your organization, and you should follow the Google's best practices, as these are very powerful. And you should avoid having too many super admin accounts. So this is covered in another session where I discuss IAM roles. So I'll include the link to that playlist as well in the description section. Now, let's talk a bit about tags or labels. Now, labels are key value pairs that you can use to organize your resources in GCP. It is very important to label your resources, because as the organization grows and your resource grows, it will be difficult for you to manage, for example, say which department uses how many VMs, or what is the cost per department that is pending, and so on. Like you can use tags and labels to organize your resources and so on. All right, so moving on, it also helps you break down your bills and so on, and you can also divide your resources by environment, by team, by product owners, by components. Say you have a front end and a back end. Now front end VMs have a certain tag, back end VMs have a certain tag, middleware VMs have a certain tag, and so on. And you can also tag it by the state. For example, if something is down, it should be tagged as down or archived, and something which is active is actively running, and so on. So labels help you segregate your resources. Now, there are also certain things known as network tags. Some people confuse network tags with labels. These are similar concepts. So labels are applied to any GCP resource, while network tags are applied only to VPC resources. We'll come deep into what a VPC or virtual private cloud is in a while. And further, there's another difference, like labels just organize resources, while network tags affect how resources work. Example, if you tag a VPC resource with a certain network tag, then a certain firewall rule may be applied based on that, and so on. So network tags are something different than just labels. Labels are just stickers to identify a certain type of resource, or a certain state, or a certain category. And they do not have any functional effects. If you tag or label a resource wrong or by mistake, nothing happens. But resources are affected with network tags, so one must be careful about that. All right, so that is about labels. Now let's talk about Cloud IAM. Now, simply put, Cloud IAM controls who can do what and on which resource. So that's a one-liner to describe IAM. So who can do what and on which resource. So resource can be a virtual machine, a database, a user, and so on. So it is important to notice that the permissions are not directly assigned to the users. Instead, they are bundled into roles, and roles are then assigned to members. So a policy is nothing but a collection of one or more bindings of a set of members to a role. So that is in very short what IAM is all about. And as I said, I'll include a playlist URL in the description, which has all these topics in detail. But as this is a crash course, this just gives you an overview or insight into the Google Cloud platform. So very concise. And if you want to take a deep dive, watch those videos and other courses available over the internet. All right, so what are identities? As we spoke about IAM, so it stands for Identity and Access Management. So let's talk about all these components. So in a GCP project, identities are represented by Google accounts created outside of GCP and defined by an email address, not necessarily Gmail address. These identities are mapped. So let's talk about a few definitions here. Now, what are Google accounts? They represents people like you, me, any engineer working on Google Cloud Platform, administrator, and so on. What are service accounts? Service accounts are used to identify non-human users. For example, application services, virtual machine, and other such users. Now, authentication process is defined in such service accounts by account keys, which can be managed by Google or by human users like us. So there is another concept called Google Groups, which is nothing but a collection of Google user and service accounts. And there is a concept called G Suite domain. So it is the type of account that you can use to identify organizations. If your organization is using Active Directory, it can be synchronized with Cloud IAM using Cloud Identity. And there is a group called All Authenticated Users. So this represents any authenticated users in GCP, and there is a group All Users, which denotes any user authenticated or not. And then comes the roles. So when we talk about roles is nothing but a collection of permissions. So there are various types of roles: primitive, predefined, and custom. So when we talk about primitive roles, the original GCP roles that apply to entire project, that is the primitive role. So primitive role can be a viewer role, a editor role, or an owner role. The editor contains viewer and owner contains editor. So if you imagine this scenario, that's how it is. And then there is a predefined role. Predefined role provides access to specific services. For example, say you have predefined a role called storage admin. So it'll have administrative privileges for storage. So, and finally, there is another type of role that is custom role, and that lets you create your own roles combining the specific permissions that you need. One thing you must remember that when assigning roles, follow the principle of least privilege and prefer predefined roles over primitive roles. So these are the two things you should keep in mind. All right, let's move on to the next thing, that is the Cloud Deployment Manager. Cloud Deployment Manager automates repeatable tasks like provisioning, configuration, and deployments for any number of machines. It is Google's infrastructure as code service. So you might have used IAC services from those in AWS world, used something called CloudFormation. You might have used Terraform to build your infrastructure as code. So Google's infrastructure as code is called the Cloud Deployment Manager. So you can use that to deploy Google Cloud resources. You can even use Terraform, but as I said, this is Google's IAC, and it is used by the GCP marketplace to create pre-configured deployments. So say you want to have a LAMP server, Linux, Apache, MySQL, PHP, or you want to have a mean stack with MongoDB and so on, and you want the template to be created infrastructure as code, you can do it with the Google Cloud Deployment Manager and use that ready-made template from the GCP marketplace. You can define your configuration in YAML files and list the resources created through API calls, and then that YAML can be deployed to create your infrastructure. So the resources are defined by the name and type and the disks and which zones they are going to be deployed into. Everything can be defined in that YAML file, and then you can deploy it. And to increase the performance, the resources are deployed in parallel. So in a matter of seconds, you get the infrastructure stand up. And in case you have certain dependencies, for example, say you want your application server to be deployed after the database is up and so on, then you can also specify your dependencies to do a sequential execution of your infrastructure as code scripts. So that is how you do it here. And you can modularize your configuration files using templates so that they can be independently updated and shared. Now, the templates can be defined in Python or Jinja 2, and the contents of the templates will be inlined in the configuration file that references them. So the deployment manager basically creates a manifest containing your original configuration and any templates that you have imported and the expanded list of all resources that you want to create. And that's how it creates your resources from the code that you define. So moving on, we will talk about cloud operations. So what is cloud operations? It is a set of tools for monitoring, logging, debugging. So basically your observability stack. So cloud operations allow you to do cloud logging. So cloud logging is GCP's centralized solution for real-time log management. And for each of your projects, it allows you to store, search, analyze, monitor, and alert logging data. And by default, this data is stored for a certain period of time. However, you can define your own retention periods and your compliance requirements. And logs can be exported to different purposes. If you want to do certain BI or you want to feed it into some machine learning to create a model and so on, these can be done. And you have various tools to create those pipelines as well. You can also create log-based metrics in cloud monitoring and get alerted whenever something goes wrong for a certain number of times if you define such rules. And logs are a named collection of logged entries. So log entries record status of events and also include the name of the log. For example, you will have a log like compute.googleapis.com/activity. So this will store the activity of Google APIs lists. And when we talk about logs, we should also discuss a bit about the types of logs. So first, there is a kind of log that are called user logs. So these are generated by the applications and services, and they are written to cloud logging using the cloud logging API. And these logs are obtained from common applications like MySQL, MongoDB, Java, Tomcat, and so on. Now, there are some other kinds of logs which are sensitive logs called security logs, which might be used for audits and so on. So these logs are not publicly, they are not available as unless you have certain policies to do that. And further, the log levels that you define sometimes incur additional costs, so you can check, and they are by default disabled, so you can check and enable them as and when needed. And so that is about logs. Apart from that, something comes into my mind is the VPC Flow Logs. So these are specific to VPC networks, and VPC Flow Logs record a sample of network flows sent from and received by VM instances, which can be later accessed in cloud logging. Now, these can be used to monitor network performance, forensics, real-time security analysis, expense optimization, and so on. So that is about logging. Now, when we talk about cloud monitoring is a Google Cloud component which lets you monitor the performance of your applications and infrastructure. It allows you to visualize your infrastructure monitoring in form of dashboards, and you can create uptime checks to do check resources if they are up or down, and based on this you can act on fixing resources in your environment. You can use Google monitoring for monitoring all your resources in Google Cloud, and also for other public clouds like AWS. So don't just think like if you create a monitoring dashboard in Google Cloud and you are a multi-cloud resource providers, GCP provides these features. So you can keep track of resources across multiple projects, across multiple clouds. So very much recommended to use this. And it also provides monitoring agents which you can install in your virtual machines to send the application metrics to the cloud monitoring. And there are other features as well, like you can have alerts based on the conditions that you set up. You can have traces. For example, if you have microservices and lots of services they're talking to each other, then it will be difficult to trace a certain call, because say there are 30 services and service 1 talks to service 5 back and forth, and 5 speaks to service number 20, and so on. Like there is a mesh of different services talking to each other. Then finding a log or checking a log for all these 30 services and making sense out of it is difficult. So for a certain call that comes in and traverses to many services, if there is a mechanism of tracing a certain call, then it is easier to detect errors. So in these cases, finding bottlenecks with your services, having a tracing tool helps a lot. So Google allows you to do that. So you have trace IDs on your log entries. So using those trace IDs, you can track a single stream of events that happens when a particular API call is made, and so on. So that is one thing. You also have error reporting that can aggregate and display errors or stack traces from the Java stack, Node.js, PHP, or whichever programming language your applications are built on. And you can debug your applications and so on. And further, Google also provides a profiler which you can enable and use to profile the CPU memory allocation for your applications. So that way you can also optimize your applications to be more performant. So that was about the observability tools. Now let's discuss how to store data in GCP. Let's discuss a bit about Google Cloud Storage. So Google Cloud Storage, as you can see in this diagram, comes in various classes or types. Now, Google Cloud Storage service is basically meant for unstructured data. So by unstructured data, I mean pictures, videos, files, scripts, database backups, and so on, like objects which you would like to place somewhere. So these objects are placed in buckets, and they inherit the permissions. I mean, if you create subfolders inside buckets, they all inherit permissions. And storage classes provide different SLAs for storing your data to maximize cost for your use case. And a bucket storage class can be changed, but it will affect the new objects added to the bucket. The pre-existing objects will not be affected if you change the storage class. And in addition to Google's console, you can interact with the Google Cloud Storage using the GS util or the Google Cloud command line. And you can specify multi-threaded updates or parallel updates when you are uploading, say, for example, large number of files or large number of small files. Like when you're uploading a large number of small files, you can use multi-threaded updates. When you're uploading a large number of uploading large files, you can do a parallel update. So that is about basically the Google Cloud Storage. And there is another option to store to upload files to GCS, that is called Storage Transfer Service, or STS. Now, STS is a mode of transfer in which you can import data into a GCS bucket from an AWS S3 bucket. Resource, I mean, this can be accessed through HTTPS, and you can also use STS to copy data from a Google Cloud Storage bucket. If you need to upload huge amounts of data from hundreds of terabytes to petabytes of data, you can also use data transfer appliance. So this is a physical appliance which is shipped to a Google facility, and then they can upload it to GCS. So this is about the storage. And what else? Also with storage, you can determine what will happen to the object, and if the object has a particular life cycle. For example, I want a file to be stored for 3 months. So I can define these policies. So after 3 months, the file is deleted. So these can be defined in form of rules and can be applied through the Google GS utils command line utility, or with REST API calls, or even through the Google Cloud Console GUI. So that's about how policies or lifecycle policies are applied. And then you can add permissions to your buckets by using your ACLs or access control lists. You can use IAM roles to grant access to buckets. All right, so to manage permissions of your cloud storage, it is good to use IAM roles, but IAM roles are for projects or bucket-wide permissions. If you need individual permissions into individual object permissions, it's better to use ACLs, access control lists. So you can use a combination of both of this to have a efficient and secure set of permissions of your Google Cloud storage components. Then there is a term called bucket lock. Bucket lock allows you to enforce a minimum retention period for objects in a bucket, and you may need this for auditing or legal reasons. So once a bucket is locked, it is sealed and cannot be unlocked. To remove, you need to first remove all the objects in the bucket, which you can only do after they have reached the retention period specified by the retention policy. Only then you can delete the bucket. So locked buckets cannot be deleted, and this is to induce safety, and you can include retention policy when you're creating the bucket under retention policy to an existing bucket as well. So this will recursively apply to existing objects in that bucket. So that is it. If you're thinking, what is the maximum retention period that can be set in a bucket? So here's a fun fact. The maximum retention period for a bucket is 100 years. So that's how long you can set it at the moment. All right, so let's move on to database management in GCP. So how are relational databases managed in GCP? The most famous and common services that are used in GCP for relational databases are the Cloud SQL and the Cloud Spanner. Now, Cloud SQL provides managed MySQL and PostgreSQL database instances on GCP. Those who have used AWS RDS, this is what it is. So each instance here is limited to a certain region, a single region, and has a maximum capacity of 30 terabytes. So this is something one has to remember if someone is preparing for exams, or for a general knowledge, if some of your clients ask, like, what is the maximum I can store? So it's 30 terabytes of storage for each instance. For Cloud SQL, and Google takes care of the installation, backup, scaling, upgrades, read replicas, and so on. So you can just provision them and manage them. And for availability reasons, replicas must be defined on the same region as the primary server. And data can be easily imported into these instances. If you're migrating from elsewhere, you can just put your SQL files into Google Cloud Storage and then import it into the database. And data can be compressed to reduce costs, and you can also directly import your GZ files, gunzip files, when you're doing a lift and shift migration. And if you need a global availability, because this is regional, then you should consider something called Cloud Spanner. So Cloud Spanner is another category of relational databases in Google Cloud, which is globally available. So you can just remember it by the name Spanner. So it spans around the globe. So that's how I remember. And Cloud SQL is the normal SQL, which is regional. All right. So as I said, Cloud Spanner is a very good choice of database when you're looking at global availability. So, however, one must remember, like, what are the right circumstances where Cloud Spanner can be a good choice? Because when chosen without proper investigation, lots of things can go wrong, and you would think that this is a terrible choice. So you should be aware before doing a Cloud Spanner migration. One should be aware that like other migrations, one cannot lift and shift databases onto Cloud Spanner. An organization that uses traditional RDBMS will have features like sequences, foreign keys, user-defined functions, triggers, stored procedures, access control lists, and all of these kind of moving parts. So migrating traditional databases to Cloud Spanner requires us to understand whether Spanner offers the same features or not. So one should be careful about all these and only then move to Cloud Spanner. All right, so what about the NoSQL managed databases in GCP? When we talk about the NoSQL databases, the first thing that comes into mind are data store, Bigtable, and memory store. So these are the basic NoSQL databases offerings. So let me first talk about data store. So Google Data Store is a completely no ops, highly scalable document database. and it is ideal for web and mobile applications, game states, product catalogs, real-time inventory, and so on. So it is great for using with your user profiles in mobile apps. If you're building a game and want to save your state, so this is a good use case. So by default, data store has a built-in index that performs that improves the performance on queries, and you can decide your own indices and composite indices and so on. So you will need extreme throughput. If you need extreme throughput, you can use a data store for that purpose. And if you want a huge number of reads, writes per second, then that takes us to the next database type, which we are going to discuss, the Bigtable. So if you have extreme throughput needed, a huge number of read writes per second, then one should use Bigtable. Now, Bigtable is also a NoSQL database, but is ideal for analytical workloads where you expect a high number of writes, reads in the milliseconds, and you want to do a business intelligence analysis, financial analysis. You want to store IoT data, like data coming in from various small probes or IoT devices all over the world. And or say you want to analyze marketing data coming in from your affiliates and so on, or how many people went into your website and clicked what, so those kind of data. So this kind of data and analysis requires creation and configuration of your nodes in a certain way, and you can add and remove nodes from your clusters with zero downtime. So Bigtable is similar to what Redshift is in AWS world. So Bigtable helps you do database analysis. And then comes another kind of NoSQL storage, that's memory store. This is similar to Redis or Memcache. So they are in-memory databases resulting in a fast performance. So like Cloud SQL, these are also regional and have a capacity of 300 gigabytes. Now here is a very good flow chart which allows you to understand what kind of database should you use based on your use case. So data is structured, use analytical. Is it analytical? Yes. Then is it low latency? Yes. Use Cloud Table, and so on. So that's how you determine, like you can spend some time, pause this video, spend some time on this flowchart to understand the various use cases and how to determine which kind of database to use based on your use case. Welcome back. My name is Prasanjit, and in today's session, we will be discussing about Google Cloud networking. So how does networking work in the Google Cloud platform? So in that context, so with that context in mind, let's start with VPCs. So what is a VPC? We all know the full form, Virtual Private Cloud. So basically, so Google VPC is a global virtual network that spans across all regions. The single VPC for an entire organization is isolated within projects. You can increase the IP space without any downtime. So these are the advantages you have in a Google Cloud VPC. And we have some key features One is a VPC network. The VPC can be automatically set up to have your virtual topology for configuring prefix ranges for your subnets and network policies. You can configure them on your own. You can expand your CIDR ranges without downtime. And you have VPC Flow Logs to capture the traffic information going in and coming towards it. And you can also use a feature called bring your own IPs, where if you have some static IPs that can be used in your Google Cloud platform. Now, Google has a network infrastructure that it uses to run its services like YouTube, Google Search, Google Maps, Gmail, Drive, and so on. So this infrastructure spans across the globe. And so with Google Cloud, we are also using the same infrastructure. So the Google Cloud infrastructure is going to be divided into various regions, and then the regions are further broken down into zones, and then there are other POPs or edge locations. So what are regions? They are independent geographical areas, at least 100 miles apart from each other, where Google hosts its data centers. So each data center, each region can have 3 or more zones. So zones are multiple individual data centers within a region. For example, you have a region US East 1A, you have a region US East, and then you can have a zone US East 1A and US East 1B, 1C, and so on. So region has multiple zones, and each zone has multiple data centers. Now, apart from that, there are certain things called edge locations or POPs, which are when expanded are known as points of presence. So points of connections between Google's network to the rest of internet. So the GCP infrastructure is designed in a way that all the traffic between the regions travels through a global private network, resulting in better security and performance. So this is not shared with others. And on the top of this infrastructure, you can build your own resources that are your VPCs, which we talked about a bit ago. And coming to that again, VPCs, as you know, are nothing but similar to what physical LANs or local area networks are. So they are, the only difference being they are software defined networks where all the traditional network concepts apply. So you have subnets or logical partitions of the network defined using the CIDR notations. So they belong to one region only, and like these subnets can span multiple zones, but they stay within one region. If you have multiple subnets, then the CIDR range should not overlap. So that is one requirement. And then you have IP addresses that can be private IP or public IP, internal, external. And for external IPs, you can use ephemeral IPs, which means once your virtual machine or resource goes down, and then it is assigned another IP. So the IP is temporary, ephemeral. And if you want a fixed IP, then you have to pay for a static IP. And in general, you need an external IP to connect to GCP services. However, in cases where you can configure private access and have only internal IPs there, you can have jump hosts through which you can access your internal IPs instead of assigning internal IPs to each of your virtual machine that you run on. So that way you keep your systems secure. And then we have firewall rules to allow or deny traffic to your virtual machines. So they can come from both incoming or ingress rules and egress rules or outgoing rules. So by default, all ingress traffic is denied and all egress traffic is allowed. Now you can have your own firewall rules to control this more granularly. And firewall rules are defined at the VPC level, but they apply to individual instances or groups of instances using network tags or IP ranges. So you define your firewall rules at a VPC level to your VPCs, but you can define with your network tags if it applies to a particular range or a particular instance or a group of instances. Moving on, let me discuss some concepts. Like you can create hybrid networks connecting your on-premise to your VPC. That is possible. When you create a project, a default network will be created with subnets in each region in auto mode. You can delete this network, but you need to create at least one network to be able to create your virtual machines. So keep this in mind when starting out. You can also create your own custom networks and where no subnets are created by default, and you have full control over the subnet creation in the custom mode. So if you don't go to the auto mode, you have to define your own CIDR ranges for your subnets. And the main goal of VPC is the separation of network resources. So a GCP project is a way to organize resources and manage permissions. So users of project A need permissions to access resources in project B. All users can access any VPC defined in any project to which they belong. Within the same VPC, resources in the subnet need to be granted access to resources in another subnet. So if there is a subnet 1 and a subnet 2, and subnet 1 needs access to subnet 2, that permission has to be granted, or you have to do some kind of peering between these subnets so that they can talk to each other. Now, in terms of IAM roles, there is a distinction between who can create network resources and who is responsible for the security of the resources. For example, a network admin role can create subnets, virtual machines, but a security admin can create firewall rules, SSL certificates, keys, and so on. So the compute instance admin role is a role which can do both of these. So there are various roles which has different granular levels of access. So you can use the role that is applicable for your use case. And finally, as usual, the quotas and limits to what you can do in a VPC is amongst them. You can there is a limit to the maximum number of VPCs in a project. You can define a limit, the maximum number of virtual machines per VPC. You can define broadcast or multicast are allowed or not. VPCs cannot use IPv6 to communicate internally, although global load balancers support IP version 6 traffic. So these are certain things you should keep in mind. Now, how to share resources between multiple VPCs, I spoke about that some time ago. So there is something called shared VPC. So shared VPC are a way to share resources between different projects in the same organization. This allows you to control billing and manage access to resources in different projects, following the principle of least privilege. If you don't do this, you will have to put all your resources in one project. So VPC sharing is very important. Now, to design a shared VPC, projects fall under 3 categories. One of them is called the host project. It is the project that hosts the common resources. There can be only one host project. And there is another called the service project, the projects that can access resources in the host project a project cannot be both host and service project at one time. And there is another called a standalone project, a project which does not make use of the shared VPC. So you will be able to communicate between resources created after you define your host and service projects. So any existing resources before this will not be a part of the shared VPC. So that was about shared VPC. Now let's talk a bit about VPC network peering. Now, shared VPCs can be used when all the projects belong to the same organization. However, just imagine a use case when you need a private communication across the VPCs. The VPCs are in projects that may belong to different organizations, or a case when you want decentralized control. That is, you don't need to define host projects, server projects, and so on. Then is there a way where your different VPCs can talk to each other? There is, and the answer is VPC peering. So that is when two different VPCs are made to talk to each other or allowed to talk to each other. Now let's discuss how we can make an on-premise infrastructure talk to the GCP infrastructure or connect through the network to the GCP infrastructure. So when that happens, there are three different ways you can do that. So one of the option is called Cloud VPN. The second option is called Cloud Interconnect, and the third is Cloud Peering. Now, each of them have different capabilities, use cases, and pricing. So based on that, you can make a decision like what suits your use case. So as I said, the challenges, say you have different cloud where some resources are there and you want to have your resources on Google Cloud interact with the resources on the other cloud. Or if you have an on-premise setup and you want your on-premise servers to be able to connect to the servers on Google Cloud. So if this is the use case, what are the options available? So let's first discuss about Cloud VPN. So Cloud VPN, with that, your traffic travels through the public internet over an encrypted tunnel. So it's just same like what we use VPN for. And each tunnel has a maximum capacity of about 3 gigs per second. And you can use maximum of 8 gigabytes per second for better performance. Now, these two categories make the VPN the cheapest option. So you can define two types of routes between your VPC and on-premise networks. So one is the static route, where you have to manually define and update them when you add a new subnet. And there is another called dynamic route, where the routes are automatically handled, defined, and updated by using a cloud router. So this uses something called a BGP or border gateway protocol. And your traffic gets encrypted and decrypted by VPN gateways. And you have a very good connection with your cloud. So traffic travels through public internet. That's the only disadvantage here. And if you need a more bandwidth and a more robust connection, then Cloud VPN would not be a good option. So what is a good option when you are looking for a robust network connection, redundancy, and all that? So then comes Cloud Interconnect. So as we know, with Cloud VPN, the traffic was flowing through public internet. With Cloud Interconnect, there is a direct physical connection of your on-premises and your VPC. So you create a hotline kind of connection, and this option will be more expensive but provides the best performance. So there are two types of cloud interconnect available: a dedicated interconnect and a partner interconnect. So a dedicated interconnect is a direct cable, you can say, connecting your infrastructure and GCP. So as the name suggests, it's dedicated only for you. So that direct cable has a capacity of 10 to 200 gigabytes per second. And one should remember that this is not available everywhere. It is available at 60 odd locations around the world. And the next option, called partner interconnect, is where you connect through a service provider. And this is more geographically available all around the world. But as a partner is involved and as it's not dedicated, there would be sharing of this bandwidth, and it is not as fast as the dedicated interconnect, and it ranges from 50 megabytes to 10 gigabytes per second. So dedicated one is 10 to 200 gigabytes per second. So that's the difference. The final option is cloud peering. So cloud peering is actually not a Google Cloud Platform service, but you can use it to connect your network to Google's network and access services like YouTube, Drive, or GCP services. So it's a common use case when you need to connect to Google but don't want to do it over the public internet. Like you want to move something to YouTube or Google Drive, but you don't want to go through the public internet. You want to go from inside the GCP to YouTube or Google Drive. So you can do that by cloud peering. So you can peer to the Google's network using cloud peering. So these are the three ways in which you can connect to Google Cloud and Google's network from your external or on-premise network. Now, moving on to the other network services, let's talk about load balancers. Now, in Google Cloud Platform, load balancers are pieces of software that distribute user requests among a group of instances. So a load balancer may have multiple backends associated with it, having rules to decide the appropriate backend for a given request. And there are different types of load balancers. They differ in the type of traffic, like HTTP traffic, it might TCP or UDP traffic. So basically, if it is a layer 7 or HTTP traffic, global load balancer handles these kind of requests, HTTPS requests, distributing traffic to multiple regions based on the user locations, and so on. And one must remember that it can receive both IPv4 and IPv6 traffic, but that is terminated at the load balancer level and proxied as IPv4 to the backends. So no IPv6 in the internal VPC network. And then there is a SSL proxy load balancer, which is also global load balancer that handles encrypted traffic and manages SSL certificates for you. Then there is a load balancer, which is TCP proxy load balancer, which is also global at a global level, has a unencrypted handles unencrypted TCP traffic. So something like SSL proxy LB doesn't preserve the client's IP, but these kind of behaviors can be changed. Then there is something called NLB, or Network Load Balancer, which is a regional load balancer that also handles TCP UDP traffic. And it is based on IP port based forwarding. And then there are internal load balancers like a network load balancer, but for the internal traffic. So these are not exposed publicly. Well, there is another component that's Cloud DNS. So that is nothing but the domain name system host for both internal and external traffic. It will map URLs to a specific IP address. So this is the only service on GCP that has 100% SLA, all time available, 100% of the time. So that's a fun fact. And then comes another important component, that's the Google Cloud CDN. So this is nothing but a content delivery network. So if you have data that does not change often, static data, images, videos, CSS files, then it makes sense to cache it close to your users. So Google Cloud CDN has 90 POPs, points of presence, to cache the data close to your end users. So your end users can pull data from the CDNs. And after the first request, the static data can be stored in the POP, and usually much closer to the user than your main servers. Thus, in subsequent requests, you can retrieve the data faster from the point of presence and reduce the load on your backend servers. So that is about Cloud CDN. So this basically summarizes the Google Cloud networking components. To take a deep dive, you can follow my other sessions that I keep uploading in my channel. Well, now that we are done with the network, let's talk a bit about the compute platform. Now, where can you run your applications in Google Cloud Platform? So there are 4 places in Google Cloud where you can basically run your compute workloads. So the first one among them is the Google Compute Engine. Then then comes the Google Kubernetes Engine, then the Google App Engine, and the Google Cloud Functions. So in the introduction, I spoke about different types of virtual machines that you can create in the Google Cloud Platform. Now let's cover about how the data is stored, what are the various kinds of disks that can be attached to the virtual machines, how the backups are done, how instances are created with all the data and configurations that we need, and so on. So let's take it a step further here and discuss more about the compute engine, or GCE. So where do we store our virtual machine data? So basically we store them in disks. Now your data stored can be on persistent disks, on local SSDs, or in cloud storage. So what is a persistent disk, first of all? So persistent disks are disks that provide durable and reliable block storage. They are not local to the machine and are attached via the network, and so you can think of them as NFS, or network file system storages, which are mounted on the virtual machines. Now this comes along with various advantages and disadvantages. Now the advantages are these disks can be resized, attached, or detached from a VM even if the instance is in use. So you can pull it from one instance, mount it on another, even at runtime, which is good. And they are highly reliable. You do not lose that data. Even as the VM goes down, you still have the disks that can survive the instance after its deletion. And if you need more space, you can just expand that disk. And if you go for higher or larger disks, you will get more performance, and so on. So being network attached, they are the disadvantages. They are less performant than local disks. So the disk I/O is not as great as local disks. So there comes in another category of disks called SSD persistent disks, which are available and are a tad bit more costly, but provide better performance, the SSD persistent disks. Now comes the local SSD. So local SSDs are attached to VMs and they provide high performance ephemeral storage. You can attach up to 375 gigabits of local SSDs to the same instance. These can be used as the root file system, and the disadvantage is if the VM is killed, these local disks are lost. So local SSDs can be attached to a machine when it is created, but you can attach both local and persistent disks to the same machine. So based on your use cases, you can choose what kind of disks you want. Now comes the cloud storage. We spoke about this extensively some time ago. So cloud storage, as we know, is the object store, and you store various static objects there in buckets and so on. But even though it is not a file system, you can use something called GCS Fuse to mount your Google Cloud buckets as file system in Linux or Mac systems. So you can upload, download data just like you do that on normal file systems. So that is another very good feature. And let's talk about backups now. Since we talked about compute and storage and disks, let's talk about backups. So how do we back up VM data as snapshots? So snapshots are backups of your disks, and to reduce space, they are created incrementally. So backup 1 contains all your disk content, and backup 2 only the data that has changed since backup 1. Backup 3 contains the data that has changed since backup 2, and so on. So this is enough to restore the state of your disk. And even though snapshots can be taken without stopping the instance, it is best practice to reduce its activity, stop writing to the disk, and flush your buffers, and then take a snapshot. So this makes the data consistent and effective when you restore it. And then we have a concept called images. Now, images refer to the operating system images needed to create the boot disks for your instances. Now, there are two types of images: public images and custom images. The public images are provided and maintained by Google, open source communities, and third-party vendors. So you can just use them and spin up your virtual machines. And the custom images are those which you created for yourself, maybe for certain projects with some customizations and so on. So you can create your own images from persistent disks and other images. So both for the same project, or it can be shared for other projects as well. You can group your images into image families to simplify your management. And for Linux-based images, you can also share them by exporting them as a tar.gz file. Now let's talk about instance groups. Instance groups lets you treat a group of instances as a single unit, and they come in two flavors. One of them is called unmanaged instance group, which are formed by a heterogeneous group of instances that require individual configuration settings. And then there is a managed instance group, which is a preferred option when possible. And the managed instance groups look the same, making it easy to configure them and create them in multiple zones. They provide high availability and replace them if they become unhealthy, and balance the traffic among them and create instances if the traffic increases. So those into AWS world might be familiar with a term called auto-scaling group. So this is just that. So to create MIGs or managed instance group, you need to define an instance template and specify your machine type, zone, OS image, startup and shutdown scripts, and so on. And instance templates are immutable. So, and you can even update your managed instance groups, and you can create a new template and deploy them. When we talk about security, there are certain other types of VMs. One of them is called shielded VM. So shielded VMs offers verifiable integrity of your compute VM systems, and you can be confident that your instances have not been compromised. So these use cases are applicable for certain kinds of banking services or services where the data security is paramount, is of paramount importance. So that is where this comes in. All right, so let's move on to the next compute type, that is the app engines. So Google App Engine is a great choice when you want to focus on your code or application development and let Google handle your infrastructure. You don't want to spin a VM or install packages on that VM, set up an environment. Basically, you just want to write code and deploy it. So if that is your use case, you just need to choose the region where your app will be deployed, and you choose what is the environment you want to deploy on, like if you're using PHP or Java and so on, and that's it. And amongst these use cases are different websites, mobile apps, gaming backends, and so on. You can easily update the version of your app that is running via command line or via Google Console, and that's how easy it is to manage. Also, if you need to deploy a risky update for your application, you can split the traffic between old and risky versions for a canary deployment, and then slowly move on your traffic if everything is well. So Google App Engine comes in two kinds of environments. One is the standard environment, and other is the flexible environment. So the standard environment is a version where you can quickly scale up and down and adjust it to your demand. And there are some programming languages supported here, common ones: PHP, Python, Java, and Go. And you do not have access to the VPC where it is deployed. It can be scaled down to 0 instances if you want. So that is the standard app engine. Now there is another app engine, there's the flexible app engine, where you can say you do not have the supported language type present in the standard. You can go for the flexible mode, where you can use the Docker containers and bring your own container images and deploy it there. So here the instances are slower and cannot be scaled down to 0, and it is suited for more consistent traffic. And apart from that, there is a built-in app engine called Memcache, which you can also use for caching if you want a dedicated cache out of the box. So that is all about App Engine that you should know before you can start using and experiencing it. Now let's move on to the very famous Google Compute Service, that's Google Kubernetes Engine. Now, for the uninitiated, Kubernetes is the most popular open source container orchestration system. This was developed by Google and made into open source project later on. So Kubernetes is very extensive topic in itself, and I'm not going to go into the nitty-gritties. You just need to know that Google Kubernetes Engine, or GKE, makes it easy to run your Kubernetes cluster on GCP. So you are not managing the Kubernetes cluster yourself, which is very difficult to do. I mean, managing the control plane and the data plane requires a lot of effort and expertise. So here you can spin up your Kubernetes cluster in a matter of few seconds and just focus on deploying your application instead of managing and maintaining that cluster, upgrading it, and so on. So Google provides container registry to store your container images, and you can think of it as a private Docker hub on your Google Cloud. And you use Cloud Build to build your images in GCP and store them on the container registry. Then Cloud Build can also import your images from Google, import your code from Google Cloud Storage or any repository like GitHub or Bitbucket, build it into Docker image, store it into registry. So it can act as a CI pipeline for you. So that is how you work on GKE to orchestrate and deploy your images. And there is another Google service called Cloud Functions. Now, you might have heard about Lambda Functions on AWS. So these are serverless, as they call it. So you don't have to worry about where it is running and what network it uses and so on. You just have to focus on the code and deploy it. And with Cloud Functions, it is easy to build event-driven microservices or event-driven services, and they just trigger a serverless function which executes, does its tasks, and stops. So it can be used to build responsive events such as uploads to a GCS bucket or messages to a pub subtopic and so on. And you are charged for the time only when your function is running in response to an event. So very useful when building event-driven architecture or event-driven microservices architecture. Now, let's go back to discuss a bit about the data part, database part. So we talked about BigQuery a bit. So how do we work with big data in Google Cloud Platform? Now, BigQuery is Google's serverless data warehousing service. Now, this provides analytics capabilities for petabyte scale databases. Now, BigQuery automatically backs up your tables, but you can always export them to GCS to be on a safe side. And you will incur some extra costs there, but it's there. And data can be ingested in batches, for instance, from a GCS bucket or from a stream, a data stream, like from a Kafka stream and so on. And it allows you to have your data in multiple formats: JSON, Parquet, CSV, or Avro. And You can query data that resides in external sources called federated sources, for example, from different Google Cloud Storage or GCS buckets. And you can interact with your BigQuery by using SQL from your Google console. You can interact with command line running queries like bgquery, and you can also interact with the data using REST APIs and also using code client libraries, say using a Python code or something. So this is about BigQuery. Now, BigQuery, something more about BigQuery is that it is a columnar data store. The records are stored in columns. The tables are collections of columns, and data sets are collections of tables in this case. And the jobs are actions to load, export, query, or copy data that BigQuery runs on your behalf. Now, there are two important concepts related to tables in BigQuery. One of them is called partition tables, and other one is cluster tables. So partition tables is to limit the amount of data that needs to be queried. Tables can be divided into partitions. This can be done based on the ingest time or including a timestamp or date column. So that way you partition your tables and query only for a certain periods without querying the full table. And then there is a type called cluster tables where data is clustered by column, for instance, order ID or any other kind of segregation. So BigQuery will perform clustering based on one or more columns there. So that is about BigQuery mostly. And let's talk about another Google Cloud service, and very important one. That's the Cloud PubSub. So PubSub is nothing but publisher subscriber for short. And PubSub is Google's fully managed queuing service, which allows you to run your applications asynchronously and decouple the publishers and subscribers. So publishers are nothing but services or events that add messages to the queue, and subscribers or consumers are ones which consume messages from the queue asynchronously. So when an event occurs, the message is instead of being consumed by the endpoint right away or being thrown up at the endpoint right away, it can be kept in a queue and processed sequentially or processed at a later time instead of at the runtime. So that saves resources and helps manage the uptime of your backend systems. So PubSub is, although similar to Kafka, is not a direct substitute. Those of you who have used Apache Kafka or RabbitMQ, they can relate to what PubSub is. And Kafka is mostly used for streaming events, but this is a bit different. So PubSub guarantees that every message will be delivered at least once, but doesn't guarantee that the messages will be processed in that order. So it is usually connected to data flow to process the data and ensure that the messages are processed and so on. And the PubSub have both pull and push mode. So in push mode, messages are sent to the subscribers, resulting in lower latency. And in the pull mode, the subscribers pull messages from the topic, and it is better suited when a large volume of messages are to be consumed. So that is about Cloud PubSub. There is another fully managed service to execute tasks asynchronously. That is called Cloud Tasks. Now, there are some differences between Cloud Tasks and Cloud PubSub. Let me tell you so that you know about this. So in PubSub, the publishers and subscribers are decoupled. So the publishers do not know anything about their subscribers. When they publish a message, they implicitly cause one or multiple subscribers to react on the publishing event. However, in Cloud Tasks, the publisher stays in control of the execution. So Cloud Tasks provide other features unavailable for PubSub, like scheduling, specific delivery times, delivery rate controls, configurable retries, access management of individual tasks in a queue, task queue management, creation, deduplication of messages, and so on. So you can say like Cloud Tasks is a bit more sophisticated version of the Cloud PubSub. So by now you might have realized like how rich Google Cloud is with very different functionalities and that fit to your use case for your application. So using Google Cloud would allow you to really create a cloud native ecosystem or cloud native application ecosystem. All right, so let's move on to some other interesting services. That is, one of them is the Cloud Data Flow. So the Cloud Data Flow is Google's managed service for stream and batch data processing. It is based on Apache Beam. So you can define pipelines that transform your data. So Cloud Data Flow is basically used for ETL processes. Okay, so for transforming, loading data. This is used when you want to do ETL tasks on your data before being ingested in another service like Bigquery, Bigtable, or to Cloud ML for creating your machine learning models. Now comes another Google Cloud service, that's the Cloud Data Proc. So it is the Hadoop and Spark service, or the managed Hadoop and Spark service, you can say, and lets you manage your Hadoop clusters easily and turn them off when you're not using them to reduce your costs. So you know how much hassle it is to build a Hadoop cluster or how much effort it needs. So here you have a managed Hadoop cluster in form of Cloud Data Proc. And there is another service which is called the Cloud Data Prep, which provides you with a web-based interface to clean and prepare your data before processing. And then that brings us to another service called Cloud Composer. So it is a fully managed Apache Airflow service, which will create, schedule, monitor, and manage workflows. So these are all specific to specific use cases, not very commonly used, but Apache Airflow is pretty famous in the open source workflow management areas. So you can just have a look at that project, Apache Airflow. And Google Cloud Composer is the answer when we are talking about Airflow. And there are some AI and machine learning services on Google Cloud. The most famous one is the AI platform, which provides you a fully managed platform to use machine learning libraries like TensorFlow. You should know that TensorFlow is also a Google project that was made open source, similar to Kubernetes. So you don't have to focus on how to run your AI platform. You just focus on how to run your AI platform. You just focus on your model, and Google will handle all the infrastructure needed to do your training. And after your model is trained, you can use it to get online and do your batch predictions and so on. Now, there is another service that is called Cloud AutoML. So there you can use models trained by Google or use your data to train their models. And then you can leverage the models to build applications that are based on NLP, speech processing, machine translation, or processing videos, getting recommendations engine from trained models, and so on. So that is about AI platform and Cloud AutoML, the machine learning part of the Google Cloud. That brings us to another segment of Google Cloud that is about how we explore and visualize data in GCP. And this is a suite of very famous Google Cloud services and very much appreciated and unique in the cloud arena. So one of them is the Google Cloud Data Studio. Data Studio lets you create visualizations and dashboards based on the data that resides in the Google services. So YouTube Analytics, Sheets, AdWords, local uploads, Google Cloud Platform data, BigQuery, Cloud SQL, GCS Spanner, many third-party services can be used to project their data on Data Studio. Now, Data Studio is not a part of the GCP, but the G Suite. So their permissions are not managed by IAM. So there are no additional costs for using Data Studio other than the storage of the data, queries in BigQuery, and so on. And the caching can be used to improve performance and reduce costs. There is another service called the Cloud Data Lab, and there is a service called Looker as well. So these all allows you to explore, analyze, and visualize data in BigQuery, ML engine, compute engine, cloud storage, Stackdriver, and so on. So very useful in terms of visualization and creating dashboards. Now, this brings us to the next section that is about security in the Google Cloud Platform. Now, let's begin with how encryption is handled in Google Cloud Platform. So Google Cloud encrypts data both at rest, that is data stored and on the disk, and in transit, that is data traveling in the network, using AES implemented via Boring SSL. You can manage the encryption keys yourself, both storing them in GCP or on-premise, or let Google handle them. So that is how encryption is done. So encryption at rest is done by default. Your data will be divided into chunks, and each chunk is distributed across different machines and encrypted with a unique key that is called the data encryption key. And the keys are generated and managed by Google, but you can also manage the key yourself. So that is how encryption at rest is done. And then is the encryption in transit, where to add an extra security layer, all the communications between two GCP services or from your infrastructure to one or more network layers, your data would not be compromised if your messages were to be intercepted. So as we spoke a little while ago about encryption at rest, so we spoke that Google encrypts the services itself and using encryption keys, and you can manage the keys themselves if you want. So to manage your own keys and their rotation policies and so on, you can use a service called Google KMS, or the Key Management Service. So using that, you can create, rotate, and destroy symmetric encryption keys. All the keys related activity is registered in logs, and these keys are referred to as customer managed encryption keys. So in GCS, these keys are used to encrypt the object's data, the objects CRC32C checksum, and the objects MD5 hash. And Google uses server-side keys to handle the rest of the metadata, including the object's name, and the DKs are used to encrypt your data, and also encrypted using single encryption keys in the process, which is called envelope encryption. And the default key rotation policy is for 90 days, but you can change that. So that is about key encryption. There is another security component called IAP, or Identity Aware Proxy. Now, Identity Aware Proxy allows you to control access to GCP applications via HTTPS without installing any VPN software or adding extra code in your application to handle login. So your applications are visible to the public internet, but only accessible to authorized users, implementing a zero trust security access model. So they are exposed, but no one can open it. They are only accessible via IAP. Furthermore, the TCP forwarding, you can prevent services like SSH to be exposed to the public internet. The next security component is called Cloud Armor. So Cloud Armor protects the infrastructure from DDoS attacks, distributed denial of service attacks. And you can define your rules, for example, to whitelist a certain IP or CIDR range, or to create a security policy based on a certain pattern, or something which is enforced at a point of presence level closer to the source of attack, and so on. And Cloud Armor gives you the option of previewing the effects of your policies before you activate them. So you can run a simulation before actually activating a policy, which is good. And then comes the cloud data loss prevention. This is a fully managed service designed to help you discover, classify, and protect sensitive data like PIIs and secrets and credentials. There is another service called the VPC Service Control, which helps prevent data exfiltration and allows you to define a perimeter around your resources that you want to protect. So you can define what services and from what networks these resources can be accessed. And the final service that we'll be discussing is about the Cloud Web Security Scanner. Now, this is a very important security service in the Google Cloud platform that can scan applications for common vulnerabilities such as passwords in plain text, invalid headers, outdated libraries, cross-site scripting, and so on. It can even scan your Docker images that you store in the Google Cloud registry. So this is pretty much about GCP resources that you would need to begin with. And there are many more services, but as we bootstrap and start learning more and taking a deeper dive into GCP services, we'll be learning more about them and knowing more about them. You can put your questions that you have in the comment section below. I'll be happy to help. And let's keep learning and keep growing in Google Cloud.